this simulation will help us to understand the different wave parameters better. So here we can see a virtual piece of rope which is fixed at one end, and this is fixed at one end and the other end is free, that is we can move it up and down. So let us start by vibrating the free end and create a transverse wave. Let's see what happens. So here we have it, waves are being produced. As you can see, the particles, there are several particles, each of them is vibrating from a fixed mean position. The straight line, this one, is the average position of all the particles. So each of the particles, this red one, this green ones, each of them is moving up and down about this average position. So let us try to understand what amplitude is. As you can see that there is a displacement for each of these particles, that is the distance from a particular the distance of a particular point from this average mean position is the displacement of the particle at a particular time. Say at this instant, the displacement of this green particle where the mouse pointer is at is the distance from this mean position to this point, which is around, say, maybe 19 centimeter. Anyway, so this is the displacement. Now the displacement of this particle, this one, is 0, and the displacement of all the points after this position is negative, that is down. So the displacement can be positive, it can be negative, depending on the direction of vibration. If it's going up, the displacement is positive. If it is going down, the displacement is negative. Now, what is amplitude? Amplitude is the maximum displacement of a particle from the rest mean position. You see, each of the particle is vibrating. They're going up and then going down, like this. They're going up and then down. So they're going up, down, but at a certain point each of the particle has maximum displacement. Say for example, look at this point. This is the maximum displacement of this particle. It does not go above this length. So the maximum displacement of the particle from the rest mean position is called the amplitude. As we go ahead with the wave, we will see that the displacement can be maximum in either direction. So here we have a positive displacement, maximum displacement, and somewhere we have negative maximum displacement. Both of them are amplitude. Now let us see what happens if we try to increase the amplitude or decrease the amplitude. So let us decrease the amplitude. You see, the maximum displacement is decreasing. It's 0 now. That is no vibration at all. The displacement is 0. The maximum displacement is 0. Now let us increase it. greater amplitude means the maximum displacement from the rest mean position is increasing. See, so this is the maximum amplitude we can give here. You see, the distance, the maximum displacement have increased significantly, as you can see. Now, as you can see that the amplitude gradually decreases. This is not an ideal case. This happens because of damping. As the wave progresses, the amplitude decreases because of the loss of energy, the dissipation of energy to the surrounding. But in ideal case, the damping will be negligible. Let us ignore damping. Now the amplitude is same throughout. See, there is no damping. The particles are moving up, they are moving down in either direction. So I hope you now understand what amplitude is. Now we will move on to frequency. Now it is a time to try to understand what frequency of a wave is all about. So now we will just see what do we understand by frequency when it applies to a wave. So what is frequency? Before we can understand frequency, let us try to follow what happens to a particle which is oscillating in a wave. Say we have a wave like this, okay? Now we know that there are infinite number of particles that are oscillating. Say this is one particle, then we will have other particles as well. Say this one. So the wave can have infinite number of particles that are oscillating. Now let us try to follow any one of these particles. Each of the particles are in a cyclic motion, that is, there. First let us assume the central mean position, that is the average mean position for this particle, which can be this one. So let us say this is the average rest mean position, that is. Now about this average position, each of these vibrating particles are in a cyclic movement. What I mean is that each of the particles are completing a cycle, that is, say starting from the rest mean position, they are going up. That is, let's start from here. Say this yellow particle is at rest. On the next instant it will move up here, then it will move up again, reach the maximum displacement, then again it is going to move down. Let's use a different color for the particles that are moving down. So it will again move down along the same path like this. Now on the negative displacement, as it will be moving down below the rest mean position, then again it will start moving up like this. Now one cycle complete, that is a particle going up, coming down, going in the negative direction, then again coming back to the zero position. So one complete cycle means it will go up, down to the negative side, then back to the zero position. So this is one complete cycle, back to where it was at the start. By the time a particle completes one complete oscillation, that is up, down, up, a wave completes a full cycle, that is half cycle, full cycle. We can say that this is the how to mark it, say this region corresponds to one full cycle. That is, by the time a particle completes one complete oscillation, the wave completes one full cycle. And this is going to take some time, right? So the frequency is the number of complete cycle that is made by a wave in 1 second. So this is what frequency is. That means if a wave moves more rapidly and completes greater number of cycles in a given time frame, then it will be said to have greater frequency. Let us try to figure out the relative frequency of different waves. Let us use a graph to demonstrate waves or to represent waves. So this is the x-axis, which shows the displacement of the particle in a wave, and let us choose another axis, that is the x-axis, that will represent the time here. Now let's start a wave. So from the point O to the point A, the wave has completed one full cycle. The particles have also completed one full cycle, that is one full oscillation. Now the time taken for this one complete cycle is called the frequency. No, this is the not the frequency, sorry, this is the time period. We'll come to that later. Now say this much is the point in the y-axis. If we represent time, say O to A is 5 seconds. That means in 5 seconds it has made one oscillation, right? And what was frequency? It was the number of complete oscillation per second. So the frequency here will be equal to 1 by 5 Hertz. This is the SI unit. Now let us have a look at an example that is much simpler than this. Let's take another graph and let us draw another wave. what you will see here is that the frequency of the wave will depend on the number of oscillation that is made per second. Say we have 1 second here. Here, this time, sorry, this one, this is say 1 second. So we see that in 1 second time it has made 2 complete oscillation. Therefore, the frequency for this transverse wave is what? 2 complete oscillation in 1 second. It is 2 Hz. What is relevant here at this point is to understand what time period is all about. Time period is the time it takes for one complete oscillation. I repeat, it is the time taken for one complete oscillation. Frequency is the number of oscillation per unit time, that is per 1 second, whereas time period, which is denoted by T, is the time for one complete oscillation. Now let us go back to these two examples. Here, as we can see in the first wave, one complete cycle from O to A takes 5 seconds. That means the time period here at this point is what? 5 seconds for one complete oscillation? It is 5 seconds. Since the time period is a measurement of the time, so the SI unit for time period is second. Now in this case we see that 2 complete cycles has been made in 1 second. So what is the time for one complete cycle? Of course, half. So here time period is equal to 0.5 second. Notice something, that the frequency and the time period are reciprocal of each other. So when the frequency was 2 Hz, time period was 1/2 second. When the time period was 5 seconds, the frequency is 1/5 Hz. That means we can say that frequency will be equal to 1 over time period. So we have covered both frequency and time period here. Now let us get back to the simulation again to understand frequency better. Now, as I said, let us try to figure out what frequency and time period is from this simulation. So we have to start the wave. So as I said before, if we follow one particular particle, we'll see that it completes a cyclic movement. That is, it is going up, then coming to the zero displacement point, then going down in the negative direction, then again back to the main position. One complete cycle. So let us increase the frequency. So if we increase the frequency, we see that there are more complete cycles for a given period of time. If we decrease the frequency, that means the number of complete cycle per second has been significantly reduced. So this is what frequency is all about, and the SI unit of frequency is Hertz, after the name of a scientist. Now the time period is the time it takes for one complete oscillation. The more the frequency, the less will be the time taken for one complete oscillation. This is obvious. I mean, this must be obvious too, because they are reciprocal of each other. So as the frequency increases, the time period decreases. Now if the number of complete cycle per unit time decreases, that means a given complete cycle will occur in a longer time, that is, the time period will increase. Now let us go and try to figure out what wavelength is. Another very important wave parameter is what we call wavelength. So what is wavelength? Now before we are in a position to understand that, let us try to look at a transverse wave deeper. Let us draw another graph that will show the displacement and the time for a wave. So here is a graph that shows the displacement on the y-axis and the time on the x-axis. Now let us try to draw a wave. It's going to look like this, of course. Now remember, the maximum points are called crest and the minimum points are called troughs for a transverse wave, and the maximum displacement point are called rarefaction in longitudinal waves. And troughs corresponds to compression region in a longitudinal waves. Now we have crest here as well and a trough here as well. Now what is wavelength? Wavelength is the peak to peak distance, or we can say it is the crest to crest distance, that is starting from here. If we go there, this is wavelength, which is usually represented by the symbol lambda. So lambda represents wavelength. Now one fact that is worth mentioning here is that the displacement time graph for a wave shows the displacement of a particle, of a particular particle with time. You see, any particle will move up and its displacement will increase in the positive direction with time. So this is what happens. The displacement for a particular particle is increasing with time in the positive direction, then the displacement is decreasing, then finally to the rest mean position, and then again it is increasing in the negative direction and then coming back to the positive direction, coming back to the mean position. That is one complete cycle. This is how the displacement of a particular particle changes. This graph looks like the shape of a transverse wave, but this is not what it is. This is not the diagram of a transverse wave. This is the graph which shows the displacement of one particular particle in the y-axis and the time in the x-axis. So what we see here is that the displacement is changing periodically like a sine wave with time, and if we can somehow measure the distance from one peak point to the adjacent one, that is the next one, the successive one, that distance is called the wavelength. And of course the unit is meter, the SI unit, and the displacement time graph for both the longitudinal wave and the transverse wave is going to be the same, because the displacement of the particle changes in the same way in both the waves. The only difference is that in the direction of the displacement of the particle and the direction of the wave motion. Now the trough to trough distance will also give us the wavelength. That is, let us use the different letters. Say this is O, this is A, this is say C, this is say B, this is D. Now if we start from O, the distance OA is the wavelength, that is from one minimum position to another minimum position, from one rest position to another rest position. So we can say that O to A distance is the wavelength, then so as the C to B, another rest to rest position, C to B, that is we will understand it better when we study phase shortly. So let us stick to this one. O to A is our wavelength, and also say this is E, this is F. So as I said before, the crest to crest distance is the wavelength. So here E to F, this distance is wavelength. And so as say this one is G, this one is H, the trough to trough distance, that is G and H, are also wavelength. So both E, F and G, H, this is crest to crest, this is trough to trough, both of these are the wavelength for this wave. How can OA be the wavelength? This is neither crest, this is neither trough. You'll get the answer in a while. To understand wavelength better, we need to have an idea about the phase of a particle in a wave. Well, the phase is one particular stage of the complete cycle. So when two particles in a wave are in the same phase, both their direction and displacement is going to be the same. So let us take a wave alright, and let us say this is the rest mean position. Now let us label some points, say A, B, C, D, E, J and say K. So I've just pinpointed the maximum and the minimum points and also the rest points. Now let us locate some intermediate points. So I ran up to K, then comes L. So let's say this is L, this is M, this is N, then this is O. Now when two particles are in the same phase, that means the displacement from the rest mean position, of course, and the direction of motion is same. That means the particles A, B, see, both of them, for both of them the displacement is same but the direction is opposite, so they are not in the same phase. Why aren't they in the same phase? See, for the particle at A and for the particle at B, both of them have got the same displacement, which is 0, but at A the particle is going up and at B the particle is going down, so the phase of these 2 points are not the same. For the particles to be in phase, the displacement has to be the same, that is the distance from the rest position, and the direction has to be the same as well, the direction of vibration. So both these criteria must be filled before we can say that the two particles are in phase. So if we look at A and B again, you will see that A and B has the same displacement, but the direction of vibration of both the particles at A and B is not the same, so they are not in the same phase. Now let us compare A with C. In A the displacement is 0, in C the displacement is 0, but at A the particle is going up and at C the particle is again going up, so the direction of vibration is same for both. That means both the direction of vibration and the displacement is same, so we have both the criteria fulfilled. We say A and C are in phase, so as L and N also. See, L the displacement is this much, N displacement is this much, but M has the same displacement, but at L and M the direction is opposite. Here the particle is going up, here the particle is going down, but at N the particle is going up again. So both L, it was L, right? Yes, it was L. This was L. So for both L and N, both the condition is again fulfilled, so we can say L and N are in phase as well. Now let us look at M and O. Here the displacement is same and the direction is same as well. Here it is going up, no, here the particle is going down, and here the particle is again going down, so both the direction of vibration and the displacement is same, so we can say that M and O is at phase with each other. So they are in phase with each other. M and O. So M and O are in phase, A and C are in phase, L and N are in phase. So what are we going to do with the points in phases? This is very important because the wavelength is actually the distance between two successive points or particles that are in phase. So the distance between A and C is the wavelength. This distance is the wavelength. And the distance between, say, L and N, this distance is the wavelength. Similarly, H and J are in the same phase, so this is the wavelength as well, the distance. Now what about D and E? D and E have the same displacement, but here the direction of vibration is downward, but here it's upward, so they are not in the same phase. So we cannot say that the distance between D and E is the wavelength, because their direction of vibration is not the same, so they are not in the same phase. So this is the concept of phase which you need to understand wavelength better. So we saw that the frequency is the number of complete oscillations or vibrations per unit time, and the SI unit of frequency is Hertz. That is what we have seen at the very beginning of this video. So the SI unit of frequency is Hertz. Which is denoted by the symbol H, Z. We have also seen that the time period for a wave is the time taken for one complete oscillation. Since this is a measure of the time, the SI unit of time period is second. And wavelength is the distance between two successive points that are in phase. Successive means one after another, that is the adjacent point, the next point in the line. So the SI unit of the wavelength must be obvious to you because it is the distance. So the SI unit of wavelength for a wave is what? Meter. And the wavelength can also be called the crest to crest distance or the trough to trough distance in the same way. The point is, if we assume a wave which will be something like this, it's not that the wavelength is just the distance between two successive crests or two successive troughs. It can be some other distance as well. It can be the distance from this point to this point, as they are in the same phase. I hope you got my point. Oh no, did you notice that I almost forgot about amplitude? Remember, amplitude is the maximum displacement from the rest mean position in either direction. We don't take the direct sign of the displacement, we just take the magnitude. So if this would represent the displacement, I mean the y-axis, the amplitude would have been this distance or this distance. It can be in the negative direction as well. So we just take the magnitude, not the direction, be it positive or negative. It can be in the either direction. Now that we have went through all the important wave parameters, let us review them in a single diagram. So let us draw a graph where we can represent a wave. Say this is the displacement axis, this is the time axis. Now let us draw a wave. It can be longitudinal, it can be transverse, because as I said before, for both the longitudinal wave and the transverse wave, the displacement time graph is going to be the same, a periodic sinusoidal graph. Oops, I forgot to use a different color. Anyways, never mind. So about wavelength, a wavelength is the distance from one peak point to the adjacent one, or to the one point, or the distance between two adjacent points that are in phase. So we can say this is the wavelength, right? So a wavelength is represented with the letter lambda, which is a Greek letter. Now talking about amplitude, that should be this distance, right? This is the amplitude for a wave, and the frequency is the time taken for one complete oscillation. No, this is a time period. So if we want to measure the time period, one complete oscillation is from this point up to this. So we can say this is the time period, now what about frequency? Frequency cannot be represented here unless we have something like this. That is frequency. Let us recall frequency. Frequency is the number of complete oscillation per 1 second. So say if this is 1 second, if this is 1 second, that means in 1 second time we have one oscillation, which means the frequency is 1 Hz. Now we cannot obtain the wavelength from a displacement time graph, because wavelength is the length or the distance between the two points that are in phase. So we don't have it in the graph, but if you could measure, or if you could somehow know the distance between these 2 points, that would have been the wavelength. So we covered wavelength, we covered amplitude, we covered time period, and we also covered frequency. Now all of them, almost all of them, could be found out both for transverse wave and longitudinal waves. But how can we get the wavelength for a transverse wave, where for longitudinal waves for which we have a series of compression and rarefaction. Let us see. Say that we have a series of compression and rarefaction. So we have rarefaction, we have compression, we have rarefaction, we have compression. And then again we have rarefaction. So how can we find the wavelength for this longitudinal wave? In order to get the wavelength for this longitudinal wave, we have to measure the distance between adjacent rarefaction region or adjacent compression region. Now, where to start? We will take the midpoint. So this is the region of rarefaction. So the middle position would be something like this approximately, and here it is going to be something like this. So this is the wavelength. And if we consider the region of compression, we can still take the midpoint from one compression to the midpoint of another adjacent compression. This is very important. The distance is taken between the adjacent ones. So this is also the wavelength. Simple. Now that we have covered almost all of the wave parameters, I would say successfully, it's time to try to understand a very important wave equation, which is the velocity of a wave is equal to the frequency multiplied by the wavelength. That means if you know any of these two quantities, you can easily find the third one. We write it like this: V is equal to F lambda. This is a very important wave equation which you might need to use every now and then. Now we also know that F is equal to 1 by T, remember? So we can also write V equal to lambda by T. We are just replacing the F, that is the frequency, with the reciprocal of the time period, that is 1 by T. That's it. This is not something different. This is the same one as this one. So that's it for this video. I hope I get even better in my next video. Till then, take care and have fun.